Hi folks, we're continuing with some Chapter 2 homework problems, and here's number 15. In 1948, the stuntman Dan Coco jumped 99.4 meters into an airbag from rest from the Vegas Hotel and Casino. When he struck the bag, he was clocked going 39 meters per second. Air resistance did have an effect on Dan. How fast would he have been going if air resistance was absent? So, first off, for part A, we want to find what would have been his final velocity with no air resistance. So final velocity is question mark. He fell, so original velocity is 0. He's accelerated by gravity at 9.8 meters per second squared, and the distance he fell was 99.4 meters. If you look at these variables, what equation pops to mind? Well, the one I like is VF squared is VO squared plus 2AX. If the original velocity is 0, this can go away immediately, and solving for VF, I can take the square root of both sides. So I'm going to end up with final velocity is going to be the square root of 2AX, and you can use this if original velocity is 0. So the final velocity would have been the square root of 2 times 9.8 meters per second squared, and he fell 99.4 meters. I'm going to grab my calculator, see what I get when I do this. So 2 times 9.8 times 99.4. Don't forget to square root that value, and I get a final velocity of 44.1 meters per second. Where do the units come from? Meters times meters are meters squared over second squared. Square root of meters squared over second squared are meters per second. That's the part A. Let's take a look at part B. Part B says, what percentage of his maximum velocity was he actually traveling? Well, 39 meters per second compared to 44.1. So that's just a simple percentage, so let's do that. 39 meters per second compared to 44.1 meters per second times 100 to turn something into a percentage. 39 divided by 44.1 times 100 to make it a percentage. Keep it in 3 sig figs. 88.4% of the velocity he would have had if there was no friction. Let's take a look at part C. Part C says this: for how long a time was Dan actually falling through the air? So how long a time was he actually falling through the air? Well, let's see what we've got. He had an original velocity of 0. He had a final velocity of 39 meters per second. He fell a distance of, and these are things that we know for certain, he fell a distance of 99.4 meters. 99.4 meters, and we're looking for time. Using this collection of variables, I am tending to use the equation X is VF plus VO divided by 2 times T. Now, if I'm solving for T, this is going to be equal to 2 times X divided by VF plus VO. How did I get that? We did this couple different problems earlier. We have done that one. So let's go ahead and put our numbers in. 2 times the 99.4 meters. Final velocity was 39 meters per second, plus the original velocity was 0. And if I put this in my calculator, 2 times 99.4 divided by 39, I end up with 5.097 seconds. Round that off to 3 sig figs, 5.10 seconds. Now, where do the units come from? Meters divided by meters per second. Meters divided by meters per second. So we're going to invert and multiply. Whoops, meters times seconds over meters. Meters cancel. I'll end up with seconds. All right, let's do one more. Let's do number 16. Melvin throws a hammer. Melvin throws a hammer straight down off a roof. 3.5 meters high with a speed of 17.2 meters per second. So he throws a hammer off the roof, and we know it is going to go a displacement of 3.50 meters, and it has an original velocity of 17.2 meters per second. How fast is it going when it hits the ground? So I'm looking for V final. It is still accelerated by gravity, so gravity is going to speed it up 9.8 meters per second squared. Now take a look at this. What equation has x, VO, VF, and AG? I'm tending to use VF squared is VO squared plus 2AX. Solving for VF, and VO is not constant, so that's not going to go away. So VF will be the square root of original velocity squared plus 2 times A times X. So I'm going to do this down here because I need some room. So final velocity will be the square root of original velocity, 17.2 meters per second quantity squared, plus 2 times 3.5 meters times, oops, I put meters where I should have put displacement, so I'll put acceleration here, 9.8 meters per second squared. I just transposed where the variables went and the numbers. So final velocity will be, and let me do this intermediate step in case you get lost just putting things in your calculator, 17.2 squared. So this ends up being 295.8, so 296 meters squared per second squared plus 2 times 3.5 times 9.8. All of this is 68.6 meters times meters, meters squared per second squared. These two values can be added because they have the same units. So we're going to look at the square root of those two, which are 365 meters squared per second squared. So if I take the square root of that, I end up with, la-di-da-di-da-di-da, I end up with a final velocity of 19.1 meters per second. And that is the end of part A. Part B asks this question. I think part B says, how long is the hammer in the air? So how long means what? Time. So part B, time is my question mark. What are we going to use for time? Lots of choices. Giving everything we have here, I think I'm going to go back to that simple equation. VF is VO plus AT. So time is going to be equivalent to final minus original divided by acceleration. Final velocity was, I got to go back and grab my numbers. Final velocity was 19.1 meters per second. Original velocity was 17.2 meters per second. And accelerated by gravity, 9.8 meters per second squared. Put all this in my calculator, and I'm going to end up with a time of, let's see, 19.1 minus 17.2 equals divided by 9.8, and I end up with time of 0.1938 or 0.194 seconds. Where do the units come from? Meters per second. Meters per second we can subtract because those are the same units, divided by meters per second squared, so invert and multiply. Seconds squared over meters, cancel, cancel, cancel one of those. Wahoo! We end up with seconds. Life is good. Okay, that should do for that one. And I think we have enough time. Let's take a look at the next one. We might have time to do one more in this video. Nope, let's do this next one in another video. Okay, we'll see you next time. Bye-bye.